Hello, everyone. Welcome to our Deep Dive podcast, where we review the latest and most impactful research papers in AI and robotics. Today, we're exploring the technical report SimpleVLA-RL, Scaling VLA Training via Reinforcement Learning, published in September 2025. Are you ready to get started?
Absolutely. This paper is quite exciting, as it addresses some of the most pressing challenges in vision-language action, or VLA, models for robotic manipulation. To kick things off, could you briefly explain what VLA models are and why they matter?
Of course, VLA models are a new paradigm in robotics that combine visual perception, language understanding, and action generation into a single, unified framework. This allows robots to interpret complex instructions, perceive their environment, and perform manipulation tasks, all in one go. The potential applications are vast, from home assistance to industrial automation.
That's fascinating, but as the paper points out, there are two major challenges with current VLA models: data scarcity and poor generalization. Can you elaborate on these issues?
Yes, these are critical bottlenecks. First, data scarcity refers to the lack of large-scale, high-quality, human-operated robotic trajectories needed for supervised fine-tuning, or SFT. Collecting such data is expensive and time-consuming, as it requires skilled operators and diverse scenarios. Second, poor generalization means that VLA models often struggle with tasks that differ from their training data, especially when there's a distribution shift.
So, even if a robot is trained to pick up a red cup from a table, it might fail if the cup is blue or the table is a different shape. That's a big limitation for real-world deployment.
Exactly. The paper draws inspiration from recent advances in large reasoning models, or LRMs, like DeepSeek R1, which have shown that reinforcement learning, or RL, can dramatically improve step-by-step reasoning. The authors ask, can RL similarly enhance the long-horizon action planning of VLA models?
That's the central question, and their answer is SimpleVLA-RL, an efficient RL framework tailored for VLA models. Let's break down how SimpleVLA-RL works. What are its main components?
SimpleVLA-RL builds upon the VERL framework, originally designed for LLMs, and adapts it for VLA models. The key innovations include VLA-specific trajectory sampling, scalable parallelization, multi-environment rendering, and optimized loss computation. These allow for efficient, end-to-end online RL training of VLA models.
That sounds like a lot of technical jargon. Let's unpack it. What does VLA-specific trajectory sampling mean in this context?
Good question. In RL, trajectory sampling refers to generating sequences of actions and observations as the agent interacts with the environment. For VLA models, this means generating diverse action sequences in response to visual and language inputs and updating the robot's state based on real-time feedback from the environment.
So, unlike LLMs, where you just generate text tokens, VLA models have to interact with a physical or simulated world, making the process more complex and computationally expensive.
Precisely. That's why the authors introduce parallel multi-environment rendering, which allows them to run many simulations at once, speeding up data collection and training.
Another key aspect is the reward modeling. The paper mentions using a simple binary outcome reward, 1 for success, 0 for failure. Why is this approach effective?
Traditional RL in robotics often relies on handcrafted, process-based rewards, which are hard to design and don't scale well. By using a simple outcome reward, SimpleVLA-RL avoids these pitfalls. The model is rewarded only if it completes the task, regardless of the specific actions taken. This encourages exploration and allows the model to discover novel strategies.
That's interesting. The paper even reports the emergence of a new behavior called push-cut, where the robot learns to push objects instead of grasping them, which wasn't present in the demonstration data.
Yes, the push-cut phenomenon is a great example of RL enabling the discovery of efficient, previously unseen behaviors. It highlights the difference between SFT, which just imitates demonstrations, and RL, which can innovate based on outcome rewards.
Let's talk about the experiments. The authors evaluate SimpleVLA-RL on three major benchmarks: Libero, RoboTwin 1.0, and RoboTwin 2.0. What are these benchmarks, and why are they important?
Libero is a simulation benchmark focused on language-guided manipulation tasks across diverse objects and environments. RoboTwin 1.0 and RoboTwin 2.0 are dual-arm manipulation benchmarks, with RoboTwin 2.0 featuring more tasks, objects, and domain randomization for robust sim-to-real transfer.
And the results are impressive. On Libero, SimpleVLA-RL boosts the average success rate from 91% to 99%, outperforming all current VLA models. On RoboTwin 1.0 and RoboTwin 2.0, it achieves significant gains over strong baselines, especially on long horizon and extra long horizon tasks.
That's right. For example, on RoboTwin 2.0, SimpleVLA-RL improves performance from 38.3% to 68.8%, a relative improvement of 80%. Even on the most challenging tasks, it consistently outperforms SFT and other state-of-the-art methods.
The paper also analyzes how SimpleVLA-RL addresses data scarcity. They show that with only one demonstration per task, RL can boost success rates from 17.3% to 91.7% on long horizon tasks. That's a huge leap.
It is. This suggests that RL can compensate for limited demonstration data by enabling trial and error exploration. The model learns from its own experiences, guided by outcome rewards, rather than relying solely on imitation.
Generalization is another key focus. The authors test how well the model performs on unseen tasks, objects, and spatial configurations. What do they find?
They find that SFT tends to overfit to the training tasks and often fails completely on unseen tasks. In contrast, SimpleVLA-RL maintains or even improves performance on unseen tasks, demonstrating strong generalization across different settings.
That's crucial for real-world deployment, where robots will inevitably encounter novel situations. Speaking of real-world, the paper includes sim-to-real experiments. How does SimpleVLA-RL perform when transferred from simulation to physical robots?
The results are promising. On 4 real-world tasks, SimpleVLA-RL improves average success rates from 17.5% to 38.5%, outperforming the RDT baseline. For instance, on the Stack Bowls task, it achieves a 70% success rate, compared to 38% for SFT and 60% for RDT.
That's a significant improvement, especially considering that the model was trained entirely in simulation. It shows the potential for scalable, low-cost RL training to enhance real-world robotic performance.
Absolutely. The paper also discusses the limitations and failure modes of SimpleVLA-RL. One key finding is that RL is only effective if the base model has some initial task competence. If the model starts with zero ability, RL cannot improve performance as there are no successful trajectories to learn from.
So, a minimal level of supervised fine-tuning is still necessary to bootstrap the process. Once the model can occasionally succeed, RL can take over and drive further improvements.
Exactly. The authors also compare their approach to related works in RL for LLMs and VLA models. They highlight the importance of exploration strategies, such as dynamic sampling, higher rollout temperature, and relaxed clipping in the policy optimization objective.
These techniques encourage the model to try diverse actions and avoid getting stuck in local optima. It's interesting to see how ideas from LLM-RL, like DAPO and GRPO, are adapted for embodied agents.
Indeed, the paper positions SimpleVLA-RL as one of the earliest systematic explorations of online RL for VLA models, with public code released for reproducibility and further research.
Before we wrap up, let's revisit the push-cut phenomenon. Why is it so significant?
Push-cut exemplifies the creative potential of RL. By focusing on outcome rewards, the model is free to discover unconventional but effective strategies, like pushing instead of grasping. This flexibility is essential for robust, adaptable robots.
It also underscores the limitations of imitation learning, which can only replicate what it has seen. RL, on the other hand, can innovate and generalize beyond the training data.
Well said. To summarize, SimpleVLA-RL is a powerful RL framework for VLA models that addresses data scarcity, enhances generalization, and enables the discovery of novel behaviors. It achieves state-of-the-art results on multiple benchmarks and shows strong sim-to-real transfer, paving the way for more autonomous and adaptable robotic systems.
That's a great summary. This paper is a significant step forward for the field of embodied AI and robotics. If you're interested in the technical details or want to try it out yourself, the code is available on GitHub.
Thank you for joining us on this in-depth review. We hope you found it informative and inspiring. Stay tuned for our next episode, where we'll continue exploring the frontiers of AI research.
Goodbye, everyone, and remember, the future of robotics is being written today, one paper at a time.
See you next time.
See you.